turn that off. Okay, so where we left off last week was we were talking about the de Broglie model. And what de Broglie did is he explained the flaw in Bohr's model. So if you guys remember, Bohr was the one that had orbitals. But his flaw was it didn't work for greater than one electron, and that there was no reason for the orbitals. So he said, this explains it. The separation in the orbitals explains why we only get line spectra, and it also explains why everything else is quantized. But there's no reason for it. There's no explanation as to why it would be quantized. De Broglie said that it was quantized simply because there is, so he fixed it by basically saying that electrons can behave like particles and waves. And he basically correlated that to the behavior of light acting like a wave most of the time, but some of its behaviors being particle in nature or quantized in nature. So that was kind of where we left off, that transition from the Bohr model to the de Broglie model. But there are some problems with de Broglie too. And these problems were pointed out by our next person, which is Heisenberg. Now, how many people have heard of Heisenberg?
Well,
He's the most what?
Well, the most speculative thing that Heisenberg is the thing. Or is that a completely different thing?
I don't think the blimp was named after him, because I think the blimp kind of came at the same time or before him.
Okay.
I don't think he was... Wait. Yeah, anyway, I thought maybe you guys would say you recognize Heisenberg simply from watching Breaking Bad, but I guess I'm wrong on that. So Heisenberg is most famous for what for his uncertainty principle. And this is where, if you ask me, quantum mechanics gets truly strange. I can kind of believe that an electron would behave like an electron. But what Heisenberg said is that basically you can't know both the momentum, and we haven't talked about momentum much in chemistry, and we're going to leave it pretty vague like that. We'll give it the symbol P because M is taken up by mass and some other things, and the position of a particle. Position, which is x of a particle with certainty. What Heisenberg argued, and is provable, is that you can't both know where something is and where it's going with certainty. If you know exactly where it is, then you don't know how fast it's moving or where it's going, basically, or its momentum that it has. And if you know exactly where the momentum is at any given time, you can't say the exact location of it, that there's some uncertainty in those measurements. And mathematically, we say that the uncertainty or the change in the x variable times the change in momentum has to be equal to at least h all over 4 pi, where h again is basically just Planck's constant. So see, that keeps coming up in a lot of places because that's fundamentally the smallest division in energy that we can tell, and so that fundamentally shows up in figuring out other things. And 4 pi is just 4 pi. And remember, the delta stands for the uncertainty, certainty in position, and we have that same uncertainty in momentum. Now that's strange because I got to be honest, I can say exactly where Haley is, right? She's sitting right where she's sitting, and I can say exactly how fast Haley is moving, which is she's not right now, right? At least if we think about, like running or driving or something like that. We could argue that if she's waving or something silly like that, that's kind of like a vibration, in a molecule, but it's not changing its position necessarily. Now, if I see a car driving down the road, I can say how fast it's going, right? And at any given point, I can kind of say exactly where it is. And the key with the Heisenberg uncertainty principle is that basically, it only applies to small objects, small as in mass objects, or very fast objects. So it's kind of like the wave nature of things in that it really only applies on, for us, the atomic scale. And so that when we look at things in a macroscopic scale, like me looking at Haley or someone else, then we don't need to worry about it at all. And so what Heisenberg's uncertainty principle said is it says that Bohr's model plus the de Broglie model, or the de Broglie fixed to it, is flawed fundamentally. Because we can't know position and momentum. Therefore, it's impossible to have a fixed orbital. Meaning that you can't say that the orbital is exactly that distance from the nucleus with any certainty. And so those orbitals, if you want to think about it, he's saying that really they have to be what I'm going to call fuzzy. And like I said, this is where things get strange. This is where I got to be honest, if I'm not reading up on my quantum mechanics and reading up on Heisenberg and all that sort of stuff, that it gets weird, where I have to go, okay, this is where I kind of lose the reason why something occurs, and certainly it's where things stop mathematically making sense. Meaning, Bohr's orbitals make sense, because we can use that Rydberg equation to calculate changes in energy, right? Waves fundamentally make sense to me in that you have to have a fixed wavelength for it to double back on itself and have constructive interference. Otherwise, you get destructive interference, or you can't get a freestanding wave. That makes sense. Heisenberg's uncertainty principle starts getting a little weird in that it's very hard for me to understand why we can't know both things at once. But it's provable, and it works. And so we have to take it sort of a little bit on faith. And then the next part, I got to be honest, is horrible. So what this is saying is because it's fuzzy, is that we have to go from a deterministic model, got to spell this guy's name right, Schroedinger, to a statistical model. So we go from sort of a model that has certain fixed values to what we call a statistical model. Statistical model, where we start saying that there's probabilities of an electron being found someplace. Now, the nice thing about the probabilities is that they always tend to degenerate to those certain fixed values if we make the measurements carefully enough. And so it's a complicated mathematical model. You have to either equate everything to lots of exponentials. You have to either use that, or you can use tensors, or you can use wave functions, all of which are beyond the scope of this class. For instance, I took a grad class, so grad school class, on just this. Where we had to solve the equations, and the equations were so hard to solve, they let us use a computer program to do the hard part of the number crunching, and all we'd get out is the pictures or the answers. And so realize that, we're going way up in the stratosphere here. I don't want you to know any of that. What I want you to simply know is that because of the Heisenberg uncertainty principle, the fact that we can't know exactly where something is and exactly where something is going, that we have to resort to this Schroedinger model, and sometimes it's called the Schroedinger equation, in order to solve and figure out where the electrons are around an atom. And so it turns out that there is no very good, clear physical model for us to think about. One of the reasons people tend to think about that Bohr model and use that one is because, I mean, how many people are kind of happy and familiar with the solar system, right? Solar system makes sense to us, right? Well, the Bohr model of the atom makes sense to us. And we can use that model 90% of the time, but we're going to take the other 10% and we're going to get those ideas from the Schroedinger equation, which is rather complicated. But the nice thing about the Schroedinger equation is even though it's complicated, most of the time it defaults to predicting behavior like the Bohr model. And so even though it's more complicated and it's got that fuzziness built into it, what we're going to do is we're going to say that it degenerates kind of gracefully into that Bohr model. And we'll show how that works. Now, because the Schroedinger equation is complicated, we're going to just use 4 parts of the Schroedinger equation. And maybe I shouldn't even say 4 parts. We'll simply call them results of the Schroedinger equation. And this is fundamentally a quantum equation, in that all of the variables are quantum in nature, meaning that they are discrete values and not continuous. And so, for instance, we can define 4 numbers that describe that equation, or 4 numbers that come out of that equation that then describe the orbitals. So the first one is going to be what we call the principal quantum number. Now, what I want you to know from this is the name, certainly the variable, and then what it represents. So what the principal quantum number represents is essentially the distance from the nucleus. It's what most closely corresponds to what we think of as a Bohr orbital. And so if we draw it like a Bohr principle, what it's saying is that if the principal quantum number is 1, that's describing the first Bohr orbital. The second quantum number would describe the second Bohr orbital. The third quantum number describes the last one. And so it's the distance from the from the nucleus, which is also basically saying it's the size of an atomic orbital. And technically, it has values from 1, 2, 3, all the way up to infinity. Now, arguably, we don't go to infinity because there's not an infinite number of elements and there's not an infinite number of places the electron can be. We really only go up to n equals 7 or so. So does that kind of make sense? Because this is where we have to have a big layer of abstraction. And so we've got this equation. I'm not even putting it on the board. Honestly, I probably couldn't put it on the board to save my life. You know, if some guy comes in, holds a gun to Jay's head and says, write the Schroedinger equation, I'd look at him and be like, yeah, whatever. Just pull the trigger now and put me out of my misery. But I can use the results, which means that it predicts the interplay of 4 variables that describe where the electrons are. And the first variable describes where the electron is. The second one is called the angular momentum quantum number. Now, what can you tell us about angular? This is kind of putting you on the spot. You don't have to tell us anything. Momentum number. But what can you tell us about angular momentum? And it's given the value of a script L. So Gabe, what have you learned about angular momentum? Okay, so it's describing the speed, right, around the orbital. So it's kind of doing the same thing here. What it really tells us, though, is not only the speed, but it tells us the shape of an orbital. So this goes beyond Bohr. Because all Bohr said is that the orbitals are really equal to spheres, right? Now, when we think about planets, we don't think about it being a sphere. It's really just a circle, right? But for an electron, it can really be a sphere. So if we think about Bohr's orbitals, they really were talking about circles if we're thinking about planets. But realize that since we're in 3 dimensions, and really planets are in 3 dimensions too, they're representing spheres. Or they can represent other shapes.
You want to know if I'm
What?
I want to know if I'm back. Technically, Earth is as smooth as a billion ball.
Yes. It's not a perfect sphere, right? It's got a little bulge in the middle. Most of us got a little bulge in the middle, to be honest. I think it comes from eating well and being healthy, and so I think the planet is eating well and being healthy. So it has values, and this is where it gets a little strange, from 0 to 1 to 2, all the way up to just n minus 1. So the idea is that L is always less than n. And what it describes is the different shapes. So if L equals 0, that's saying our orbital looks like a sphere. So, you can imagine a sort of 3-dimensional sphere like that. That's not a very good picture. You can draw and find better pictures here when we talk about it. If L equals 1, it turns out that we get dumbbells. So if that's our nucleus, we get an orbital that looks like a bunch of dumbbells. Now, it kind of looks like 2 big spheres on either side of each other, and depending upon how you draw them, the shape can differ just a tiny little bit. If I have L equal 2, then I get what I call 4-leaf clovers. And so I get something that looks like it has a set of 2 dumbbells, or so basically it's 4 orbitals like that. And we'll go into some more detail here in a little bit because it does get a little funkier than that too. And then if we have 3, that's too complicated. And there's various shapes with 6 or 8 lobes. But we ignore that. Meaning we know it's there, we'll talk about it, we'll maybe even show you a picture of it for fun, but we won't use it because it's too complicated. Is that okay with you guys? That we at some point just cut things off and say, wow, that's ugly looking, let's not talk about it? Okay, so then we have the magnetic quantum number. And that's given this m sub L. And this is basically describes the orientation in space of an orbital. And actually, we will take a break here in a moment, and I'll actually go get the stinking models from the cabinet. I didn't realize we were this close to talking about this. And it has values of m sub L equal to 0, plus or minus 1, plus or minus 2, all the way up to plus or minus whatever the L value is. So notice that the n quantum number is by itself. The m quantum number, or the L quantum number depends on the n one, and the m sub L depends on L. So they all have a dependency on each other. And it's that chain of dependencies that will give us the actual shapes of the orbitals. So let me go grab those from the cabinet. good model or a good picture is worth 1,000 words. So here's the shape. Sure, that's okay. So what we're going to see is that depending upon the shape, depending upon the magnetic quantum number, and depending upon the angular momentum quantum number, it predicts a bunch of different things. And then there's one last number, but we're going to save it for last because it's the easiest one to do, but it's the hardest one to conceive of. So what we're saying is that if I have n equal 1, so we're going to have our column for n, then we can have our L quantum number, and we can have our M sub L quantum number. So if n equals 1, what value can L have? It can have 0, right? And if L is 0, what value can M sub L have? It can only have the value of 0, right? It can only go up to 0 plus or minus whatever L is, and if L is 0, then M sub L is 0, right? What this predicts for the shape of an orbital is a simple sphere like this. And so we're going to have a shorthand notation for this, where we have 1, and then we call that an s orbital. So this would be the 1s orbital, meaning it's got a principal quantum number 1. The s tells me the L quantum number. And then notice we don't worry about the M sub L quantum number. We don't care about the orientation to a certain extent. One of the reasons we don't care about the orientation is that at this level, we can't tell which direction it is anyway. Plus, I got to be honest, for a sphere, there is no orientation, right? So,
What was in my periodic table in high school, I had a bunch of numbers you telling me they're different.
1s2, 2s2.
Yeah.
Yes, exactly. We're going to get to the whole string of those in a minute. So here's my sphere, right? It's a little tiny and it's pink, and I don't know, apparently Gabe's the only one paying attention. So Gabe, here's my sphere. Then, if we go to the next quantum number up, which really means the next orbital out, right? We have 2. Now, what value can L have here? It has to be for between 0 and n minus 1, right? So now it can have 2 values. It can either have a 0 value or a 1 value, right? So this is kind of what we're going to call that second set of orbitals. And for the 0 value, M sub L can only have 0. But for the 1 value, M sub L can have 0, and it can have plus 1, and it's allowed to have minus 1, right? Because it's up to plus or minus L. So the 2, 0, 0 quantum set of quantum numbers also describes a sphere, but it's further out. And so we can call that our 2s orbital. And the idea is that here's our 1s. Here's our 2s further out. Now, remember, the shape predicted by L is dumbbells. And so what that really means is we're going to call those our 2. And if they're dumbbells, they are given the symbol P. Now, the reason they're given the symbol P is it really stands for primary line, meaning if we look at the line spectrum, it's the dumbbell-shaped orbitals that give those bright colors on it. And so if you look at that, if I've got a dumbbell like this, I can have 3 orientations with it, right? I can have it kind of along the x-axis. If I think about the y-axis coming out between you and I, it can be along the y-axis, right? And if I put a third axis up, that's the z-axis, then I can have one facing up. And so what I really get for the dumbbell orbitals is that there's 3 different orientations from it. There's along the x-axis, along the y-axis, and along that z-axis. And so what we really get is a set of 3p orbitals, or I shouldn't say 3p, that's the bad way to phrase it. We get a set of 3 orbitals that depend on direction. And where did I set the pen? Bring it over here. Yes. So what the M sub L quantum number is saying is that I've got one orbital. Well, here, let's do it this way. If I draw, here's my great 3-dimensional drawing skills. So here I've got the x-axis, the y-axis, and the z-axis. It's saying I've got one set along the x. I've got another set along the y. In fact, here, we'll do this. Since Jay's got the ability to draw in color, why not? So here's my y. And then I've got a third set that's oriented along the z-axis. So electrons are weird. They're not in pretty shaped orbitals like Bohr actually has, unless they're in the 1s or 2s orbitals. But in some of the other orbitals, they get to have those weird, funny dumbbell shapes. Now, if you look at it, if you make these orbitals fat enough, it approximates a sphere, right? So, you know, it kind of approximates it, but it also says that electrons are stuck in very specific locations in that sphere. And that's what's weird about quantum mechanics, is it predicts all these weird shapes. But the neat thing we're going to find out about quantum mechanics is it also predicts the shape of molecules, which is something that you couldn't do just by overlapping spheres, because spheres can overlap in any orientation, right? But the p orbitals start to give us some preferred orientations. Okay, so there's actually 3 p orbitals, and sometimes we write them out as 2px, 2py, and 2pz. But we should really realize is that we just never really worry about whether they're which direction oriented, and so most of the time we just group them together and say the 2p orbitals. But we should realize that there are really 3 separate 2p orbitals. So if we keep going and kind of filling in this chart, then if I have principal quantum number 3, well, I can have L equals 0, 1, or 2 now, right? As long as it's less than 3. And for m sub L values, that means I get 0, 0, plus 1, and minus 1. And then for this new one, I get 0, plus 1, minus 1, plus 2, minus 2. And so notice that the 3, 0, 0 simply implies a sphere that's even bigger now. And that's what we'll call our 3s orbital. It just means that bigger and bigger spheres, kind of like those Russian dolls that nest inside each other. We get what we call a 3p orbital, which means that there's a second set of dumbbells that are just bigger than the first set of dumbbells, but they have the same orientation. And then we get this new set of orbitals, which we're going to call the 3d. Now the d stands for diffuse, but it also stands for kind of that number 2. So you can think about, you know, 0 is s, and 1 is p, and 2 is d. And so we get the 3d orbitals. And because there's 5 numbers for the m sub L, that means there's really 5 orientations. And here's where my drawing skills suck. So that's why I have the models here. For those of you that aren't in class today but listening to this, you'll have to come in and check the models out. I mean, there's pictures in your book I'll refer you to. There's pictures on the internet. So the idea is, remember I said they have 4 lobes, right? So here's one with 4 lobes. Here's another one with 4 lobes. The difference is what set of axes they're on, or bisect, right? So if I take a look at it, I can come up with 4 different orientations very easily. So here that's like this. Notice that that's 45 degrees off, right? And then that one's like this. This one can be perpendicular like this, right? So all those have different orientations. And here's the weird thing. We get one that instead of having 4 lobes only has 2, and this weird disk in the middle. Makes no sense, doesn't it? Now notice, we could say that this is plus 1, minus 1, plus 2, minus 2. That must be the one that is singular, with 0 on, right? And so quantum mechanics predicts this funky shape. And the beautiful thing about quantum mechanics is it predicts this funky shape, and then when you go out and look at how atoms bond together, this funky shape really exists. Meaning we can actually see it in action almost. I mean, we can't physically see the orbital, but we can see how it affects the shape of molecules and stuff. And so that d orbitals is where things start to get kind of funky. And so we've got 5 of them, and they're given designations like, for instance, we can say that we've got the 3d xy, the 3d xz, and then we can got that weird one, which is actually called the 3dz squared. But again, we don't worry about that. We're simply going to lump them together and talk about 3d orbitals and not worry about their orientation, because that's a step beyond what we want to go. Now, let's finish that column off with one last example. And that's if I have quantum number 4. Because now we can have 0, 1, 2, and 3. And we know that this is 0, 0 plus or minus 1, 0 plus or minus 1, plus or minus 2, plus or minus 3. Oops, not 3. That's the next one. 0 plus or minus 1, plus or minus 2, plus or minus 3. And so this predicts the sphere. This predicts 3 dumbbells. This predicts 5 clover leafs, with one of them being an oddball, we're not going to worry about. This predicts 7 what we call F orbitals, and these are the ones with 6 lobes or more. So if you look, I have an example of a few of them, but I don't even have all 7. I don't even know where the other 3 or 4 are. But you know, that's not too bad, but then when you start to line them up and say, well, that's got that orientation, this must have this orientation. Actually, that's not even in the right spot. Ignore that one. I don't know how that got in. But you can see where the 7 orientations get too confusing to look at. Now, we can pull up a picture of that on the internet and take a look at it. And I think I even have one stored on my computer, but since I'm on the wrong computer, we'll just go and Google it quick, because Google's our friend, assuming my computer doesn't slow down. Notice I was looking up de Broglie. Not an exactly handsome-looking fellow, perhaps, but I think he has looking kind of beady eyes. But if we look up the shapes of orbitals, then we can certainly come up with better pictures than Jay could ever draw. And what you'll notice, though, is that also we're going to get a whole variety of different ways to draw these. So let's see if we can find one that looks pretty. So here you go. We'll just pull this puppy up. Just take me to it. Visit view image. Just give it to me. So notice, here's my s orbital at the top. That's just a sphere. Notice that I've got these p orbitals. Now notice that they label them different. Instead of labeling them px, py, or pz, and py, they label them p minus 1, 0, and 1. That's just telling you the m sub l quantum number, right? There's 3 of those. Notice that we've got our d orbitals. They've got 4 lobes, and then that funky one in the middle that says d0 that looks like just 2 with a circle in it. And then we've got more. And then notice we've got all of our f orbitals. Those start to look funky. The f0 orbital actually has 2 lobes and now 2 rings. So to me, that's one of those things where it's like, okay, that's what the math proves, and we can actually see molecules that make use of that, but honestly, it's too funky. And then we've got all the other pictures with lobes. And so we're going to ignore those lobes. What I want you to know, or what I want you to take from this, is the general picture of the s, p, and d orbitals. I don't want you to worry about f's too hard. I mean, what's the chances of me asking you to draw the f orbitals on a test? 0. What's the chance of me asking you to draw s, p, or d? 100%. Now, which one of those 3 I ask you to draw? I don't know. If you want to take your chances and only draw spheres, then you got a 1 in 3 shot of getting it right. And then what I also want you to take home is those different quantum numbers. So if we take a look at it, for instance, this says that there is, you know, a set of s orbitals. And then the next furthest out is a set of s orbitals, but there's also a set of p orbitals that are out that far. And then we have to go out further still to get to the 3rd shell. And so we're kind of constantly building this. Now, I did leave out one quantum number, because theoretically it's difficult, but experimentally, or when we're writing things, it's pretty easy. It's called the electron spin quantum number. And it's given the value m sub s. And it does not depend on the other 4 quantum numbers. It simply says that m sub s equals plus 1/2 or minus 1/2. So there's only 2 options. And the way people describe it is that it can be thought of as that the electron spins in space, in which case it can go clockwise or counterclockwise. Or the other way you can think about it is the magnetic field for one of them points up, whereas the magnetic field for the other one points down. And so there is a part of each atom, or the electron cloud, that interacts with magnetic fields. Now, we kind of knew that anyway, because we know that, for instance, from the Crookes tube experiments, that electrons are deflected one way or the other, right? What this is saying is that the same thing can be said for atoms. This was done by the Stern-Gerlach experiment, Gerlach, in which he took silver, which has 47 electrons. Therefore, half of the silver has an electric field going up, and half of the silver atoms have the opposite electric field, or should have it pointing down. And what he did is he took those atoms and he passed it through a magnetic field. And one half of the atoms were pointed up, and one half of the atoms went down. And so, you know, how you want to interpret the magnetic spin quantum number is kind of up to you. Really, what we only care about is that it has two values, one where the magnetic field is up, one where the magnetic field is down. We're not going to say which one is up and which one is down. And so we just really have to realize that it has two values. So this is also responsible for what we call the splitting of the line spectra. So if you take a look at line spectra, it really turns out that there are two values that are almost identical, and that if you have good enough resolution, you can see that every one of those values is actually doubled. And that doubling comes from whether the plus 1/2 or the minus 1/2 is excited. So let's compare this to the Bohr model. And the best way we can do that is to take our orbital in our Schroedinger model, or we'll really call it just the quantum model. And so, for instance, if he talks about a 1s orbital, that predicts a sphere of density. And perhaps I should point out, and let's see if we can find a good picture of it. Those spheres are drawn as having one specific distance. What we have to realize is that the distance we are from the nucleus is fuzzy based on Heisenberg's uncertainty principle. And so really what we want to do is kind of think about orbitals more like this picture here, where there are actually fuzziness to them, meaning that instead of saying it's a very well-defined sphere, I really should say it's a sphere and then it's kind of fuzzy. So maybe we should say it's a fuzzy sphere. Not sure I can say that 5 times fast. And so if I take a look and I graph the probability of finding an electron, and I plot the distance from the nucleus, what the Bohr model predicts is that there's one specific distance for the electron shell. What the fixes that both Heisenberg and the Schroedinger model make is, again, that this is a probability, or it's a little fuzzy. And what that does to our orbital in that model is it says that it's a probability, that there's a maximum distance of finding it, but you could find it a little closer to the nucleus, and you could find it a little further away from the nucleus. So that probability density is fuzzy. Now it turns out that the maximum value, or the maximum chance of finding it, is the same as the Bohr model. So that's what I mean by it degenerates to a certain extent to predict the Bohr model. It just says that it's a little weirder than that, that there is not one fixed value, but a probability distribution, or a broadening of that line. And so that means that all of the math associated with this is harder. It means that the bonding between atoms and how electrons are around an atom is really much, much more complicated than we would ever want it to be. And that when we're going to deal with the shapes of molecules and little things like that, we're going to make and use a lot of simplifications to get us the shapes and the pictures. And then what we'll do when we talk about it in that chapter is we'll say, okay, so here's the base model. Gets us about 95% of the information we'd ever want. With a more complicated model, we can get to 99%. With an even more complicated model, we can get to 99.9% maybe. But I got to be honest, we don't need that extra 4.5% or so that the really complicated models get us for a first level chemistry class or for a first year chemistry class. And so what we'll do is we'll present that base model. We'll use that base model for 90% of what we do. We'll talk about the more complicated models, talk about why we would need them, and then kind of ignore them for the rest of the semester. So we're going to almost always drop back to the basic idea of the Bohr model. Maybe we'll mix in a little bit of that Heisenberg Schrodinger uncertainty part of it, and then not worry about it. And so what that means is like a 2s orbital, according to Schrodinger, you know, it's further out. So here's my 1s, and here's my 2s. So if I look at the probability for a 2s, so this is for a 2s electron, this is the distance, this is the probability. It actually has, here's my distance for a 1s. It actually has a little bit of density before it. It actually has a node where that is, and then it has a very high probability of density somewhere further out. And so that's the distance for a 2s. Or this would be the Bohr first orbital and the Bohr second orbital. And so it's weird in that quantum mechanics predicts that the electron in the 2s orbital actually has a small percentage chance of being closer to the nucleus than the 1s orbital. It's very small. I probably am vastly exaggerating it by even making the hump look that big. It's probably more like, you know, 1 bajillion to 1. But, you know, there's a small probability that it could be. And so that's what those probabilities that make everything difficult. And so again, we're not going to worry about them. We're going to default to falling back to that orbital. So what this says then is that we've got a series of orbitals. Oops, series. Got to spell it right. To describe where electrons are. And what it's saying is that the first set of 4 quantum numbers, for instance, if I go 0, 0, I can have plus a half, and I can have 1, 0, 0, minus 1/2, meaning that I've got m, l, m sub l, and m sub s. That's the first set of numbers that I can come out with. What this predicts is that there are 2 electrons in a spherical orbital. And then if I do my second set of quantum numbers, that's 2, 0, 0, a half, and 2, 0, 0, minus a half. So notice what I'm doing is I'm taking that chart I drew before, and instead of drawing the whole chart out, I'm just listing the numbers. But, you know, this corresponded to my 1s orbital. This corresponds to the 2s orbital. And this says that there's also 2 electrons in a spherical orbital. But it's further out from the 1s. But I also had a second set of numbers. I had the 2, 1, 0, a half, 2, 1, 0, minus a half. I could have 2, 1, minus 1, 0, a half, 2, minus 1, 0, minus a half. I could have the 2, and I could have the L quantum number be 0, 0. Wait, oops. Sorry. Let me straighten this out. Got my numbers mixed up. They're all going to be 2 1s. What changes is I can have 0, 0 there, or I can have plus 1, or I can have minus 1, in the third one. And so notice that, you know, these all stay the same. What's changing is that m sub l quantum number, and that's the orientation of the dumbbell. And so what that's really saying is that I've got the two p orbitals and that there's 6 electrons in them in dumbbell-shaped orbitals. Oops, shaped orbitals. Now I'm going to take a shortcut here, and we're going to shortcut the 3D orbitals, but Gabe, you're still writing, so you want me to pause for a second? Just let me know when you got that down. So Nathan, are you done with the homework yet? Just checking. Haley, you're working on math? I understand. You can always listen to the lecture, right? And I assume that you are. Yeah, we already talked about that. I'm just filling time because I'm waiting for Gabe. Okay, so the idea is that we also have those 3s orbitals. We're going to have the 3p orbitals, right? So, you know, I've got 2 electrons in a sphere, but it's further out again. I've got 6 electrons in those dumbbell shapes, but again, it's further out. And then what we could have is we had the 3d orbitals, and we said that there's 5 orbitals, and then of course there's times 2 electrons per orbital because of the m sub l value. So the idea is that I can have 3, 3, 3, 3, 3. There's going to be 5 sets of them, right? They're all going to have a 2 because that's the d orbitals. And then here I can have 0, plus 1, minus 1, plus 2, and minus 2. And then, of course, the last one is always just either a half, and then there's a corresponding set that's like 3, 2, 0, minus a half. And so what that means is there's really 10 electrons in the funky D-shaped orbitals. So notice I've got a pattern. I've got 2, 6, 10, and if we continue it, the F's would give us 14. So what I want to pull up now is the periodic table. And what is, let's go just grab one off of the ChemHaven. Where's my periodic table? Here's my periodic table. Might take a second to pop up. There it is. So I want you to notice the shape of a periodic table. Notice this first set of columns here has two elements wide, right? The very next set of ones is 6 elements wide, right? This set is 10 elements wide, right? And this set is 14 elements wide down here in the F orbitals. And so the idea is that this first set of columns are really elements that all have electrons in s orbitals as their outermost electrons in the picture. The ones that have over here all have electrons in those p orbitals as the electrons that are furthest away from the nucleus. The ones in the center section here that we said were the transition metals all have electrons in d orbitals. And then down here, the actinoids and the lanthanoids, those are that 14 columns. That's where they all have electrons in the f orbitals. And so the idea is that the periodic table's shape is a direct reflection of quantum mechanics and what quantum mechanics predicts. And the fact that quantum mechanics, when no other theory can predict the shape of the periodic table, if nothing else, that's what always convinced me that quantum mechanics must be a realistic theory or the best theory to describe things. Bohr's orbital theory could not explain the shape of the periodic table. De Broglie's fixed to it where he simply says, okay, you know, the Bohr model is correct, it's just that we have to explain why the electrons are in orbitals because of the fact that they're waves and constructive and destructive interference, that's wonderful. Still doesn't have anywhere near predicting a periodic table. Only quantum mechanics can predict the shape of that periodic table. So do you see how that 2, 6, 10, and 14 are pretty important? And what that really means, for instance, is that if we look at hydrogen, that has 1 electron, and so we could call that electron being in the 1s1 orbital. And that simply means that the electron is in the first sphere, right? If we go to the next element, helium, that's got 2 electrons. We're going to say that that has 2s2. I'm sorry, 1s2. Oops, it has 2 electrons. This is the 1. And so that means that in that first orbital, it has 2 electrons, right? And then if... Okay, I'll do one more atom just to kind of finish the trend before we do it. Lithium has 3 electrons. That means it's got 2 electrons in the first orbital, and then that's filled up. And it's got 1 electron in the second orbital. So it's saying that I've got the picture like this. It's got 2 electrons here, and then further out in the next orbital it has 1 electron. So notice that both lithium and we'll do it this way, hydrogen and lithium have 1 electron in the outermost s orbital. And one thing that we said is that elements in columns have similar chemical and physical properties, right? Similar, at least for instance, chemical properties. Meaning that if we make a molecule, for instance, we can say HCl, we know that we can make LiCl. And then if we keep going down, that Na would behave exactly the same way. Well, the reason they behave exactly the same way is the electron that's furthest away, the one that's most likely to make a bond or get gained or lost in a reaction, is the same in hydrogen and lithium. And so one of the things that quantum mechanics also explains very neatly is why elements in the same columns behave very similar to each other. And we'll take a look at this in more detail when we have more time, but we kind of ended here. So let's take a look at the rest of the week. We've got Monday, Tuesday, Wednesday, Thursday, Friday. So this is going to be what I call Lab X. It's basically on spectroscopy. And notice there is a pre-lab. I think you are more than capable of reading the lab and at least finishing the very easy questions in the pre-lab, the first ones. Yes. Well, you got both, but the pre-lab is the last page of the normal lab. So the idea is that you read the lab, complete the pre-lab, and bring it in tomorrow to show that you read the lab. We also will say that on Wednesday we're going to have homework 5A, 5B, 5C. Now 5A and B you could have done over the weekend. You were certainly had enough knowledge from lectures to do that. And now you've actually got enough to start doing 5D. We won't say that you can necessarily turn it in, but you ought to be able to do most of 5D for Wednesday. And then Thursday, of course, we'll talk about Lab X. And Friday, and Wednesday, we're just going to keep lecturing in quantum mechanics. So let's just turn this off because there needs to be no personal information like this set up. So let me turn it off.